Okay, so yeah, thank you so much for coming today. I know it's a very cold day and it's very late, so I do really appreciate you all coming here for the Responsible AI workshop for UTMIST. My name is Matthew Tamura. I'm going to be the main one organizing the Responsible AI workshop. I also have four other associates, Anaya being one of them, a member of the audience, and the other ones you'll get to meet over the course of the workshop series. So yeah, I guess we'll start things off with a land acknowledgement. So we wish to acknowledge this land on which the University of Toronto operates. For thousands of years, it has been the traditional land of the Huron-Wendat, the Seneca, and the Mississaugas of the Credit. Today, this meeting place is still the home to many Indigenous people from across Turtle Island, and we are grateful to have the opportunity to learn, work, and discuss on this land. Okay, so yeah, let's kind of go into an introduction to responsible AI in the first place. So if we look at what we see in the world today with the adoption and use of AI, one of the major issues that we see in the press and in the world around us is there's these harms being done by AI systems being integrated into various aspects of society. This could be caused, but like there's different, yeah, ranging degrees of this, such as using AIs in systems such as legal or medical or health instances where it doesn't operate as intended, causing certain forms of harms, or with more kind of like lower level kind of issues of AIs like breaching applications and having yeah, so like causing discrepancies or causing things to operate in a way that isn't intended. So one of the main things that we have as a question is how can we build, deploy, and use these systems for better? And how should we kind of analyze what is right and wrong and where these moral harms kind of occur? So the kind of overall solution to this is responsible AI, hence the responsible AI workshop. But I guess this kind of opens up the question of what exactly is responsible AI? Over the course of like the development of the field of responsible AI, which has been kind of occurring over the course of like past 15-ish kind of years, although early on responsible AI, I would say wasn't like classically classified as responsible AI, but would be called other things like statistical fairness, statistical ethics, human computer interaction. But all of these can kind of been over time been reframed into the field of responsible AI as we know it today. So the early fragmented view was early on when AI started being implemented out into the world. We saw a lot of instances where people would do reports or independent studies, realizing, oh, this AI system is like, such as the work of like Deborah Raji, seeing like, oh, this AI system, maybe this like facial detection system didn't has like disparities in performance over certain genders or ethnicities, or oh, this like organization is using their data for AI systems in a way that they didn't actually disclose that they're using it in this kind of way. So then there was this early view of what responsible AI was kind of like these independent fixes of isolated technical factors. Loosely connected to some moral harms and ethical principles. But nowadays, we have a much more holistic view as to what responsible AI is. So this kind of view takes the perspective of AI over the whole life cycle. So this generally is practices and principles for developing, deploying, and monitoring AI applications consistent with user values, expectations, organizational values, and societal laws and norms. So kind of central to this view of seeing responsible AI as it is known kind of in more modern kind of literature and out in the world is responsible AI isn't just requires looking at AI systems not as just the technical systems themselves, but also understanding of the complex socio-technical system and the instance and the culture in which that technology is being implemented within. So in terms of like, I wanted to kind of start off by giving like a taxonomy of responsible AI, but then the more I tried to do that, I realized it's quite difficult. There's not really any like clear there are clear fields within the field of responsible AI, but it's not really easy to kind of pick them apart. This is also due, in fact, because of responsible AI being kind of an amalgamation of different types of fields. So you have like statistics, philosophy, ethics, applied ethics, but then you also have like very technical fields like pure computation, mathematics, all that kind of stuff. So the way that I've kind of presented it for you here is we have more principle focused components of responsible AI, such as algorithmic fairness, transparency, explainability, and privacy, which are very much localize the problem to how does the AI system perform with respect to this principle. And then there's these more holistic views as to like responsible AI, such as human-centered AI, governance, accountability, and AI alignment, which asks broader questions about how are the people overall as a whole impacted by these systems, and how do these systems align with the morals and the values of the people that they are impacted by. So over the course of this workshop, we'll kind of be exchanging between principle focus and holistic focus, because to get a proper view of like responsible AI in its entirety, you kind of need both. One of the also common framings of responsible AI in industry is responsible AI as a bridge to adoption. So while a lot of this workshop will be focused on kind of like the more moral components of it and kind of like the philosophical, ethical, and mathematical questions of how do we like formalize issues in responsible AI, out there in industry, if any of you are interested in working in the field of responsible AI, it's typically framed from this perspective of how do we build AI systems such that they generate reliable outputs and so that they can capture people's trust. Because I don't know how many of you know this, but one of the major issues in Canada in terms of like adoption of AI technology is a tendency for Canadians to be kind of more risk averse and concerns that AI systems have a lot of issues and are untrustworthy and that kind of stuff. So if you look at like Canadian Board of Commerce, in 2024, they published a study that said like they think that like AI can drastically help improve the AI economy, but that's not really going to happen because everyone is too risk averse and people will not are too hesitant to adopt these technologies. And KPMG last year kind of released a similar study that showcased that Canadian economies and certain businesses are very, very risk averse. So yeah, people generally see in industry as responsible AI having this kind of value to the whole kind of AI ecosystem as a whole. Okay, now I'm going to go over a bit of brief administration. So this is how the Responsible AI Workshop series is going to be laid out. So today is just like giving a brief introduction and then diving into algorithmic fairness. Week 2 is going to be a bit more technical. So it's going to be talked about transparency and explainability, so methods that you can use to understand what are the internal workings out of how AI systems are working, as well as computational techniques in AI privacy, such as machine unlearning and differential privacy, which are techniques used in practice to just improve privacy performance of existing systems. And then week 3 is where we kind of dive into more of the human-centered facing side of things, where we talk about AI governance. So this includes how do we actually ensure responsible AI happens in terms of policy and the world around us. In the real world, human-centered AI, which is focused on how are people actually impacted by AI systems, and how you can use AI to understand people's experiences with those systems. And then AI alignment, which is focused on how do you make sure that the values that AI systems possess are in alignment with the values that people have in its applications. Also, a huge part of AI alignment is like catastrophic risk. So, oh, sorry. So yeah, so ensuring that AIs don't like become evil and destroy the world. Yeah, very, very fun part of responsible AI. So yeah, my name is Matthew Tamura. So I'm a final year engineering science student who did a specialty in machine intelligence, and I also did a minor in philosophy. So I have a bit of like philosophical background into this kind of stuff as well. A lot of my research over the past few years has been focused on various fields and endeavors within the field of responsible AI. So I'm doing research in AI at the Human Centered Data Science Lab. I do like research in AI governance at the American Psychiatric Association. I was also a co-founder of a company that did internal AI governance. Yeah, the company's still running, but I ended up leaving the company. But it gave me a lot of perspective as to how responsible AI is framed in industry and how kind of modern day Canadian like policy kind of exists around that. If you ever want to send me an email, or if you have questions about any of this stuff, that's my email. So there's going to be 3 sessions. So today's session, and there's one next week and the week after that, and it's the same room each time. It says 7 to 9 p.m., but I'll try to make it a bit shorter just because I don't want to like force you on campus out in the cold for too long. On week 3, we also have some other presenters. So we have Anita Du, who is a very talented individual. She knows a lot about AI governance. Alden Arciaga and Anaya Amir, that's Anaya, who are going to talk about human-centered interaction and human-centered AI. And Divi Wadhwani, who is going to talk about AI alignment. So yeah, let's dive into algorithmic fairness. So algorithmic fairness is one of the main kind of principles or principle of fairness in terms of responsible AI that people have been concerned about over the past couple of years. There's been many cases of algorithms having unfair outputs, as I'm sure many of you have heard. But one of the most famous cases is with the case of Compass. So who here knows what like recidivism is, or what recidivism is? Okay, yeah, I know Anaya knows what that is. But basically, recidivism is basically like when someone who's committed a crime like does another crime after that. So what the Compass algorithm did is it was an algorithm that was used to create risk scores based off of like 31 characteristics of individuals' information to predict if they're what's the risk of them reoffending again in the future. So this algorithm in particularly, out of like all the algorithms out there in the world, sparked one of the probably the biggest controversy and like issues within the field of responsible AI and AI fairness, because of a study done by an organization called ProPublica, ProPublica, a nonprofit that analyzed the outputs of this system and realized that there was a huge kind of disparity the in the algorithm's assignment of risk for people who are like Black as opposed to white. So then they were like, wow, like how could they implement this system into like legal practices with this form of bias? And then the Compass algorithm creators were like, wait a second, that can't be right because we did our own internal report with the same data that you all had, but we found that the data set is fair. So then this sparked this major controversy as to like, how do you actually go about measuring algorithmic fairness? Because you can have these same data sets, but based on the metrics you use, you can have different views as to like, is that information fair or unfair? So this kind of like sparked a whole debate in the field of responsible AI, which we'll kind of dive into today. Okay, so before we kind of go into things, I just want to do a bit of like a primary discussion for a few minutes to just kind of get a sense of like what you kind of believe or understand with the concept of fairness. So I guess like with the people around you, so I guess if you guys bunch together and y'all bunch together, I briefly discuss like the question of like how would you go about defining fairness and unfairness, and what do you think makes unfairness if ever morally wrong? And also, can you have unfairness without moral wrongness? Also, we're a small enough group that I feel like we could also just do this all together. Um, Actually, yeah. Would you prefer doing it all together or just like individually? Or yeah, yeah. Okay, that's my original idea. Okay, so sure, you can bundle up, and then I'll get back to you in like a few minutes. Okay. We're gonna take it all up together. So I guess like yeah, does anyone want to answer as to like how you went about defining fairness? I know that group had a couple of different answers. Assume they should start. Like we should start. Okay. Does anyone want to present? I can also, if all of you are uncomfortable, I can also just share some things that you said. Yep, A. Oh, I can go ahead. Okay. So I think there were two notions of unfairness that were talked about. So one was like about like different distributions across like for different people. So like one focused on more of the effects, and another notion of unfairness that's more about the process. So about like using characteristics about an individual, like their race or ethnicity, to make judgments over a decision. So yeah, those are the two main like formalisms of fairness, unfairness on that group. Same thing? Okay. Yeah, those are like the two highest like level categories of unfairness. And I guess the question of like what makes it, if ever, morally wrong. I feel like your group was debating about that a lot, so I'm interested in hearing your perspectives. Which discussion did you overhear that I Oh, you were all like talking about like distributions and stuff. So yes, like let's say we randomly and a random process we kind of agree was a fair process, right? If everything is completely random. So we randomly initialize an I as a millionaire and a millionaire for 100,000 dinner. He has a $0 dinner, right? So let's say we're all taxed because an I said equality is kind of the definition of fairness. So let's say everyone has to pay the same amount of taxes. It's like an equal, it's a flatline tax. Is that fair? was the kind of where that discussion was going before it's not. So was that morally wrong? I would personally say no, because that's just like I got cooked and I kind of have to deal with that. But we were going with that discussion, we didn't get to mention. Okay. Did you have thoughts about that, I guess? So wait, is that morally wrong? So is the question about like equality versus equity, basically? So you're bringing up or that equality was like a pretty good benchmark for fairness, right? Right. You wanna- I was gonna say, I guess what we define it is that perfect fairness is perfect equality. It's not like morally wrong. It's morally wrong when it involves people mostly. That's like probably. Yeah, I guess there's a question of like if there's action done against people, like is it just like undisputedly like affecting certain individuals in a way which like compromises any component of their like personhood or ability. And I guess like technically, if you do that, then I think you could say it's okay from that lens. But then if it's like if someone's like really struggling and they're forced to pay these taxes while everyone else is supposed to pay the equal taxes, then there's kind of like distributional harm with respect to that because the experienced effects of certain individuals is not equivalent to the experienced effects of others, even though it's the same policy. Yeah. So it ultimately depends on the lens which you use. Well, I guess you could say mathematically the results result in mathematical fairness, but then in terms of experience, like harm-based fairness, then that's like different. It depends on like what definition of like fairness has to attend to some form of like field, be it like purely statistical, purely like impact based, like it has to tend to somewhere. So it's hard to say that like it is like an overall fair policy unless yeah, you can also maybe it's like too like obscure, but it's like I would say something is fair if there's a one-to-one mapping and it's a linear mapping between point A and point B, and that mapping linear such that essentially everything that's being manipulated is manipulated by the same amount. So that means that when you apply the policy, it's fair there, and then the output is fair as well. Okay, I think you might like a certain form of fairness that gets presented later. But I think that's very similar to calibration, if you ever heard of that term in algorithmic fairness. But yeah, like in terms of conceptions of unfairness, these are the generally like common categories that typically show up in fairness literature, in like pure fairness literature, like ethics. So there's like comparative notions of fairness. So one of the main ones discussed here was like carrier oriented, which is like what are the impacts on disadvantaged versus advantaged groups. But then there's also kind of this version of fairness that Abdul's kind of pointing towards, which is a very epistemic form of unfairness, which is like what is that like mapping between the mathematical like base rates and the distributions to the like technology and the algorithms itself. So the general way that they frame it as a fairness issue is they say that like using evidence differently in virtue of differing group membership. So it's like that basically means that like risk scores, actually I'll talk about it later, but it's basically the same notion that Abdul is pointing towards. And epistemic here just means like philosophy of knowledge, so like knowledge based. And then there's also some like non outcome oriented views of fairness that also exist. So some of those could include like yeah, so these are just generally like procedural versions of fairness. So like decisions based on a group to individual inference. So that's basically like stuff where it's making generalizations about people, that kind of stuff. Unfairness is inaccuracy. So like one thing is if I was like doing a race against other people, and then when they're like timing it, they use a really, really inaccurate like timer. Like I could say like, oh, that's really unfair that you use this like crappy equipment for my race thing for something that's so important. So in that sense, inaccuracy can be a form of unfairness. And then there's also more procedural ones such as fairness as right to explanation, and then fairness by unfairness by the means through which outcomes are being kind of decided, such as judgment. So in algorithmic literature, you'll typically see like fairness grouped into two different categories. So one is group fairness. So it's groups defined by protected attributes receive similar outcomes and treatments. So this is very similar to like a lot of the framings of fairness that we share today. And then there's also individual fairness, which is completely agnostic to groups. So just saying in general, like similar individuals receive similar outcomes and treatments. So it's not looking at groups at all, but you do need some sort of like metric of similarity for individual fairness. So as you can see, like in like literature reviews or like systemic reviews on the literature, these are the more common ways of that fairness is framed. So for today's workshop, I'm going to mostly focus on three types of them. Also, like you don't see individual fairness as much. Counterfactual fairness is something that sometimes shows up, but it's in really specific models. In general, like the metrics for group fairness are ones that you can kind of apply across different models and scenarios. So yeah, before going into the different formulations of algorithmic fairness, I just want to briefly talk about false positives, true positives, false negatives. Like how many of you have like seen this before? Okay, so pretty much like everyone on this side and some people on this side. So basically, there's something called a confusion matrix when you have a result. So when you have like your model does things correctly, where it says like this is a true outcome, and then it actually is a true outcome, you got a true positive. So it's like if you see a hot dog and it actually is a hot dog, that's a true positive. False negatives is actually false positives is you think it's a positive, but it's not actually a positive. So that includes like if your model is detecting hot dogs and it sees this dog that looks like a hot dog and thinks that's a hot dog, that's a false positive. Predicted negative is it's it's uh it's not supposed to be negative, but you identify it as negative. So typically it's a case like the data is such that it looks like it corresponds to a negative case, such as um yeah, like clearly not a hot dog, and then it is not a hot dog. And then there's true negatives where it's like it's not a hot dog and it's not a hot dog, so everything's good. So basically, the accurate ones are the ones across the diagonal, while the ones on the other diagonal are inaccurate. So yeah, usually you see that sometimes with actually yeah, I'll go into this first. So one of the main ways of formalizing the problem of algorithmic unfairness is with demographic parity. So basically what this just means is if you have a predictor and you have some form of attribute. So basically this means like this is just basic statistical notation. So if everything like right up the line is stuff that's like your prior, so stuff you knew before, and then everything left is like what the actual outcome is. So basically, with or without some predicted attribute, such as like race, gender, that kind of stuff, the outcome remains the same. Uh, so this basically just means that across different, like, yeah, like protected attributes, the result, your predictions are like the same. So in that sense, it's like it's doing the same thing across groups. So what might be like an issue with this metric that some of you might be able to see in terms of like measuring fairness? Like across different distributions of attributes, would you expect any given like variable to be the same always across those? Oh, wait, is that a hand? No? Okay. Okay, so like basically what this is saying is if you have any one characteristic and you change it, and then you have some other variable, and you would expect the probability of those things being like that same output as the same. So, oh, yeah, Jessica. Sorry? Yeah, it's basically like it's saying that there's independence across all variables or across the protected attribute. So let me try to think of a way of yeah, okay, I'll just talk about the issue. So basically this just assumes that the distribution of that data with respect to those variables are always the same, which for that measure of fairness to make sense. Because otherwise, if there's any difference in the base rates, like the rates of different things occurring, then that form of fairness isn't gonna work. Like if I just say like um what's an example? base rates. If I have like, hmm, I don't think of a really simple example. Okay, let's say I'm like going through different rooms of a house and I'm trying to figure out like which room has the most fruit. So obviously like the distribution, so like if I have a prediction that like if my model is fair, it'll predict, actually, does that make sense? I'm trying to think of like a very non-applied example, but I think a lot of them are applied examples. But basically, like if there's any distributional difference of a group, so like if, for example, I guess for like crime, for example, statistically with the base rate, there's a lot more like black people that are incarcerated versus white people that are incarcerated. So if you have an algorithm, so that's just like a baseline statistic that is out there. So if you have a model that just predicts like the chance of someone being a criminal, of being like given that they're black and white and the prediction being the same, you would assume that that's incorrect, right? Because it doesn't match the reality of what the underlying like correspondence between that characteristic and the outcome. So even if your model is, yeah, so in that sense, like that model wouldn't be um
It's incorrectly mapping a feature. It's incorrectly mapping a feature to a certain outcome. So it's like correlation, causation.
yeah, it's like it's basically being overly prescriptive as to what you should expect for fairness. It's like saying that the probabilities of someone being this characteristic based off of like maybe race or gender should be the same. But that's just also not a map of reality because with respect to certain characteristics, just the like baseline statistics of like how much of those people have certain people have certain attributes are just different statistically. Yeah. Um, yeah. Okay. So basically, to avoid that issue, I think that issue that thing will also be better. It'll be there's other things later on which will describe that a bit better, I think. But yeah, so to avoid that issue, instead of focusing purely based off of stuff which can be influenced on base rates, we can also base things off of false negatives and true positives. So this is what equalized odds is. So it's more concerned instead of just like um the predictions itself of like what they're outputting, they're instead concerned about how often are you making um like false predictions on that data. So yeah, so that's like kind of a different way of doing it to kind of get around that. And then the other main way of doing it is calibration. So calibration is basically says that for each given possible risk score, the expected percentage of individuals who are actually positive is the same for each relevant group. So that just means that like if I have my like if it was Compass, for example, if the model predicted like you got a 0.6 um prediction for having like being someone who's gonna cause another crime in the future, that basically just means that given that output, there is like in reality a 60% chance of me actually having that. So what calibration says that should be what those statistical mappings between the risk score and the actual percentage chance that someone is going to do something should be exactly the same. And this kind of goes back to the notion of epistemic unfairness because it's like if you have different risk scores, but they have actual different mappings to the actual percentage chance that someone's going to do something, then that means you have to use that risk score information in a different kind of way where you're kind of assuming some form of bias is like, oh, I think this risk score for this certain group is actually going to correspond to like a real higher percentage or a lower higher percentage. So that's why calibration is kind of relevant there. Yeah, so here's like a brief little exercise to kind of show you how calibration works. Um, So, okay, I'll give you a hint. But like the block line, for example, is something that is perfectly calibrated because for the output distributions, the corresponding outputs on the line map perfectly to the true probabilities in terms of percentages. So if something has like a risk score of 30%, then the true probability of that thing happening is 30%. So any deviation across this for different groups means that it is an uncalibrated algorithm. Um, so one of the issues with calibration is you can kind of mess with it and kind of cheat the results. So in this case, for example, you have a red line where you have some sort of consequence threshold where it's like if you're above a certain risk score, then something's going to happen. So you see that in instances such as like automated decision systems where it's like if they automatically like screen your stuff and you exceed a certain threshold, then that'll ensure that some human reviewer will actually review your document or something you do. But you can kind of game it. So if you just add a bunch of like noise to your distribution that you outputted, um, and then you pass it through into a logistic regression model. Basically, that just means you globally lose information. So then the distribution kind of centers more around the mean. So then you can kind of mess with calibration in a way by just basically the general idea is you can mess with calibration to kind of serve your purposes. So it's a metric that people should kind of use with some level of caution because, yeah, people can kind of just mess with it post hoc. So the kind of presentations of the different forms of unfairness are kind of map with some of the definitions of unfairness that we presented. So both of these are kind of conceptions of comparative fairness. So parity and equalized odds are more focused on care-oriented fairness because it looks at the impacts on disadvantaged versus advantaged groups. More so with equalized odds because that's specifically looking at the impacts of when you're doing a false positive or a false negative and what kind of entails in the systems upon making those false judgments. Well, calibration is more focused on like how well your data output matches to the underlying statistical um, distribution of the real world data. So in the case of Compass, the reason why there's kind of that open space for people to have that debate in the first place was because it was a model that was really well calibrated. So as you can see, like similar to the calibration curve that I shared before, this is the one that they actually had for Compass and the one that the creators of Compass actually released. If you see for any corresponding risk score, the chance of recidivism for that individual is roughly similar to white and black individuals. However, if you use other conceptions of fairness, such as like equalized odds and parity, which looks at maybe like false negative rates and false positive rates, you see that there's a big discrepancy there, where there's a lot of like, for false positive rates, there's a lot of African Americans who have a higher rate, which means that they think that they're more likely to predict people who have who that say that they are gonna cause crimes in the future if they know that that person's African American and the false negative rates are a lot higher for Caucasian, which basically means that they're more likely to say that that person isn't going to commit a crime if they're white in the future, even if they are. So then there's this kind of like issue of um, what conception of fairness is kind of the correct one to use in this instance, because both of these like forms of fairness have mathematical grounds. Um, but which one, like, does this actually signify a greater issue if one is being met and the other isn't being met? So this kind of um, mathematical issue can kind of be looked upon further by just exploring another metric, such as false discovery rate, which has some rough mappings to calibration. But basically, the relationship that I want you to pay attention to, oh, and also because it has a relationship to calibration, performance false discovery rate is roughly the same across different races. So for yeah, so to mathematically kind of relate these three metrics together, you see that that you can see that you can represent false positive rate, false negative rate, false discovery rate, and prevalence, which is just like the fraction of the population that actually have ones in the population. So that in this case, it means people who are gonna the chance of given no other information, just the chance that based off of race that they are going to be someone that will cause a crime again in the future. Yeah, you can see that they're all related. Um, so suppose that like prevalence is unequal between groups, which is generally something that you can assume because data distributions tend to be different across um, different groups of identities. And FDR, like false discovery rate, is equal across groups. Then what does that imply about false negative rate and false positive rate? So this is a bit of a mathematical thing. So it's basically like if you know that this is not the same between two different groups, and then you know that this is equal across the groups. Um, what do you know about false negative rate and false positive rate? Oh, yep, Abdul.
Um, in one case, one is gonna be higher, the other, it's gonna be like that.
Yeah, exactly. Like one's always going to have to be higher than the other ones. So mathematically speaking, this is called the impossibility theorem, where if where basically you can't have all metrics be the same for algorithmic fairness. So that basically means that the only case where you can have perfect like values across different protected attributes or races is if the algorithm is a perfect predictor and has like 0% error, or the base rates of the outcome is exactly the same, which almost like never occurs in reality. So then this kind of like motivates the issue of how do we select the correct form of algorithmic fairness or like equation of algorithmic fairness to evaluate a given situation. There's also like a direct there's also a paper that directly talks about this in terms of calibration and fairness, where here there are two curves. Like I won't talk about the mathematics behind this, but here there are two curves, like the blue line and the red line represent perfectly calibrated algorithm outcomes for two different groups. And they have to match those relations because there's a mathematical formula between base rates and parity. So if you want to have, and then the y-axis is false negative rates and the x-axis is false positive rates. So if you want to have equal false positive rates, then it says that you have to be on this dotted line. So then on the two like parity achieved outputs of the algorithms, you can see that they all kind of fall here. But then by matching false positive rate and parity, then you have difference in false negative rate. And similarly, if you have matching false negative rate and parity, you don't have false positive rate. So you basically can't always, it's impossible to achieve perfect outcomes across different fairness metrics. So then this has kind of created a lot of debate in academic settings and industry settings as to like, how do we actually go about measuring fairness, quote unquote, the right way? And there's not a lot of consensus over this. Like there's been law review papers out there which are like, we don't know what to do. So that also becomes a downstream issue because if they don't have academic consensus, then they can't really give any guidance on for existing models out there. And like, this is how we should, like, we know that it's important to not have algorithmic unfairness, but they don't know the exact technique or way of measuring algorithmic unfairness. It's not a lot of like practical guidance. Um, so yeah, so this is just kind of like an ongoing issue, has been ongoing for like the past couple of years in the field of algorithmic unfairness of how do we find the right metric. So there's been multiple attempts of trying to justify like why this metric is better than the other metric. One of like the ones that I find funny is like this philosophy paper called On Statistical Criteria of Algorithmic Fairness, which follows a similar setup to lots of papers that you'll see if you look in the field of algorithmic fairness, where it's like they create this toy scenario of with like a distribution of different like data, and then say like, okay, I have a perfect model and when I apply it to this data, here are the outputs on all these different metrics. And be like, oh, I know that my model is fair and my data is just my data, but I see that these metrics are saying that it's unfair when it clearly is fair. So this model is bad. So that's a very typical way of like arguing for a certain form of metric. But there's a lot of like issues with that because um, if you just look at purely the mathematical, then you kind of miss the downstream impacts of these fairness decisions that actually happen in the world. So there's also been a lot of work done in trying to like look at algorithmic fairness through that lens and try to understand that given a certain social situation or given the certain outcomes that an algorithm might have, how should we kind of look at fairness in that context? So one of the ways that Carnegie Mellon University has gone about doing this is creating something called a fairness tree, where it kind of has like a bunch of different decisions that an algorithmic designer themselves can kind of go through to kind of determine what conceptualization of fairness should they go about when creating this algorithm. So as you can kind of like follow along, there's just like a bunch of different questions, and then ultimately it'll lead you to a certain conception of algorithmic fairness to be used. Um, there's also a paper that's quite important called the Possibility of Fairness, Revisiting the Impossibility Theorem in Practice, which basically says like all of you mathematical people have been wrong all along because you don't really need perfect fairness or perfect values across all the different metrics. As long as you have some form of error that um, you're willing to kind of live with, or is some level of like discrepancy between the values across different metrics, you can actually create a lot of algorithmic solutions that are compatible with like multiple definitions of algorithmic fairness. So this paper was like to show that basically what this diagram represents is how much difference between the metrics you're willing to kind of live with. Along the perfect diagonals, that just means like this is the x and y axis are prevalence. So it's like differing base rates. So if the base rates are the same, you just expect them to see good performance. So that's why like all the diagonals are lit up. But as you can see, as you kind of create more room for error, you'll get more solutions that kind of divert away from the diagonal in the middle, which basically indicates models that have general good performance, if not perfect performance across the different metrics, but just good enough metrics, good enough performance. Um, do you all want to take like a brief break? Because it's been an hour, but if you want to keep on going, we can keep on going. Okay, sure. I guess we'll keep on going. Okay, here's a little case scenario to kind of get you thinking about like metrics in practice. Uh, I can read it out or you can all read it, but it's basically a cancer screening AI system is used to predict future risk of lung cancer. It has a performance gap between black and white patients. It has lower recall. So recall is just like uh so recall um retrieved. So I'll just say like so given uh okay, I'll do yeah, recall is this true positive of over true positive plus false positive. So it's called recall because like if you the algorithm retrieved it or like flagged it as like this is something like there is cancer, what is the chance that that is actually true? So basically for a certain group, it has lower recall, meaning that it routinely underestimates the risk of cancer, classifying patients as low risk. Well, eventually, yeah, who will eventually develop lung cancer. Um, and then yeah, anyone who's subject to high risks um, are subject to further checks. So there's no way to kind of improve performance for Black patients. The only way is to equalize performance, which means to reduce the performance for white patients, lowering both their recall and accuracy. So I guess why? Okay, I guess yeah. So I guess the first question is why focus on recall here as opposed to general error rate parity or calibration? Um, to answer this question, I'd like think about like the effects of being classified as a true positive versus a true negative. So like if given that the system like classifies all like high risk people as subject to further checks, why why might that lend well to recall? Okay, I can also answer this question if it's a bit difficult.
Wait, so it's the first question, more focus, recall, as opposed to error rate?
Yeah.
It means that if you have like recall being one, so that means that every single time there's a true positive, you're correctly detecting it. And I guess that matters. Wait, why focus on recall here as opposed to general error rate, parity, or calibration? You'd want to catch cases of that rather than let them slip by. Like it's fine to do extra screening, but it's better to catch those things rather than just let them slip by.
Yeah, that's exactly it. It's because the dangers of doing a false positive, which recall doesn't really account for, that false positive. Oh, sorry, I just wrong. True positive. Yeah. The dangers of doing
That's fine.
false negative. So basically saying that, so in a case where someone doesn't actually won't actually develop lung cancer, but they were screened by the algorithm, all that entails is that just means that they are subject to further checks. So that's not that bad. But if someone who will develop lung cancer isn't subject to further checks, that's pretty bad because that means you've like missed someone who needs medical care. So in that sense, like this is why this system is like conceptualizing or like choosing to conceptualize fairness in terms of or like performance in terms of recall. So I guess the second question is, should they go ahead and reduce the performance on white patients to achieve parity across the black and white groups? You can, oh, yep, go ahead. Yep. So exactly. So certain members of that population would like they would feel like they would experience the issues of not being identified, which basically means that yeah, they're not getting like the care that they're supposed to get. So I guess like this comes into question like why does this override the notion of fairness? So this is kind of partially why I also went back to the discussion of what is morally wrong about unfairness. Because here it's like there's a clear unfairness in the group, but it's kind of evidently clear that that unfairness is okay if it's the goal of it is to kind of like avoid harms to people as a whole. Um, so yeah, there's some sort of like moral conceptions of like how we should think about fairness. Like one of the more common ones is the thing that's fundamentally wrong about unfairness isn't some intrinsic thing, but it's about the harms that occur as a consequence of those forms of unfairness. So if harms are occurring and actually you achieve less harms by having some form of unfairness, then in that case it's like morally okay. So that's sort of what we see here. But then there's also this issue of like um, if people are just looking through a pure fairness lens, that they might miss kind of like the broader issues and harms that are occurring. This kind of issue of reducing performance for the higher performing group under the guise of fairness is known as leveling down. So it's basically, yeah, when you reduce the performance of privileged groups and then in the with the goal of fairness. And this is actually something that you see being done um, within actual ML systems, which is kind of a bit concerning because that means that they're not really properly thinking of why they're using fairness in the first place. So like in computer vision systems, like this paper looked at a couple of different computer vision systems and saw that in the actual development of these systems, to have equalized performance across different groups, they actually went about reducing overall performance so that for specifically for certain groups, just to achieve that fairness metrics. And a similar thing can be seen in the IBM AI Fairness 360 UCI adult data set. So IBM has kind of like an automatic tool for doing algorithmic fairness stuff, or like a toolkit for you to use certain metrics and techniques for algorithmic fairness. And I found that in like the default settings for that, this form of leveling down is something that does occur by default for some of the settings. So this kind of points towards something called Goodhart's law, which is a measure becomes a target. When a measure becomes a target, it ceases to be a good measure. So all these conceptual mathematical conceptualizations of fairness are aimed at pointing you towards like ultimately doing less like moral wrong against these different forms of people, but just purely optimizing for fairness for the sake of fairness and kind of leave people to overlook certain issues that actually do occur. Um, yeah, there's another issue that we kind of face with respect to fairness is we tend to kind of I'll skip to the answer of this. We try to focus on comparative forms of fairness in algorithmic fairness in computer science and engineering, specifically on either calibration and impacts on disadvantaged groups. But a lot of the times, the extent to which impacts are looked at are not really beyond just the outputs of the system itself. And when you kind of look at those impacts as a whole, that's where a lot of unfairness actually occurs. So let's revisit the case of Compass for a final time. So there's a famous legal case that actually arose from the use of the Compass algorithm. So someone named Eric Loomis, he was charged with 5 criminal accounts related to a drive-by shooting. Ultimately, he was only like convicted of 2 because they found proof that he was in the car, but that he didn't shoot people. And at his sentence hearing, the trial court used Compass algorithm as like a resource and as evidence to say that this person should have this sentence. So the Loomis themselves and their legal team filed a motion to say like, hey, this doesn't seem right. You can't use the outputs of this risk prediction algorithm to say that my sentencing should be made like more severe. Like that shouldn't be like a form of evidence which you base your decision off of. That's just supposed to like help you. So then they argued that this is a violation of their due process rights. Specifically, the way that they argued that is infringe on the rights to an individualized sentence, infringe on the rights to be sentenced on accurate information, and also that the court unconstitutionally considered gender at sentencing by relying on risk assessment that took gender into account. So that third point was very much based off of the ProPublica report, which showed the discrepancies between race and gender of race. They also showed discrepancies in gender for the algorithm. So that's kind of like where that argument came in. But a lot of the arguments, I think all 3 of those arguments were denied. Honestly, some of the arguments weren't that like accurate in the first place. Like clearly, I don't think they really understood how the algorithm works with like infringement to a right to an individual sentence, because that got overruled because they used the data of Loomis to make that sentence. So they're like, oh, it was individualized. And the right to be sentenced on accurate information, they're like, oh, well, our performance metrics are high enough. So if you say that AI systems are overall unreliable, well, we have empirical evidence to show otherwise. But the court that did deal with this issue did say like overall other people in legal systems must be should be aware of like when not to use yeah, that these risk scores created by Compass and similar algorithms should not be used to determine whether an offender is incarcerated or determine the severity of the sentence. So is there anything like, does anyone kind of like disagree with any of the elements of this outcome or have any thoughts generally? It's okay if you don't as well, because this is only like a thin slices of what kind of happened. Oh, yep, go ahead. Hmm. Yeah. Yeah, I think that's a really good point. I think this kind of goes back to, yeah, like one of the issues of unfairness of when you look through people through the lens of just general specific characteristics and data, then you are not really looking at the individual and their circumstances specifically, but just looking at core components of their data and just assuming that that's how that person is and should be represented as an individual within a legal system. Um, so yeah, I think there definitely is like there I feel like there definitely is an argument where that I feel like that could have won. But in this specific court ruling, they just said it was sufficient enough, which is also like unsatisfactory. I feel like it's a bit unsatisfying because it's like then what is sufficient to like fully capture like what amount of information about an individual is fully sufficient or insufficient to say that it's an individualized sentence for that person. Because yeah, as you said, there is an element of generalization and non-individualization here. Um, and I think that's also one of the main outcomes of this legal case, which was like put people the wrong way. It's like you say that the court says like they should not be used to determine whether an offender is incarcerated. Well, then how the heck are you supposed to use this algorithm in the first place? Because you get like these courts are given this risk assessment tool and are like, hey, this is to help you make your decisions. But then they're not supposed to use it to figure out if someone's incarcerated. So then, like, what are they supposed to use it for? And naturally, if you present these algorithms, the outputs of Compass to people, like the by giving it them, there's some assumed meaning that it is there to be used in that decision making process. So that's one of the main kind of issues with respect to Compass that never really got any form of closure is there's just an overall like lack of guidance as to how to even use this algorithm in the first place, which causes unintended consequences, detrimental consequences as a result of the issues of fairness of that system. So this is kind of why one of the main points that we brought up in the responsible AI slide was like algorithmic fairness requires understanding of not just the technical, but also the broader socio-technical system, like how the algorithm is actually being adopted, how the algorithm is actually being used by the people using that algorithm, and are they aware of like how to use that in a responsible way, in a way that is in alignment with like what the outputs should be doing. So this kind of like opens up two different views of algorithmic fairness. So one is weak fairness, which is just focused on like debiasing algorithmic systems. So this is like a lot of what we were talking about today is like weak fairness because it's about like you have an algorithm, you figure out if it's unfair or fair, and then you're like, oh, let's make it unfair. But then there's another form of fairness called like strong fairness, which is trying to design algorithms to actively and proactively challenge like the oppression within society and oppression towards individuals and having that awareness of where that algorithm fits within the broader system and to make the society itself a bit more a bit more fair. So in certain fields of computer science, you do see this conception of fairness a bit more. So this is something you'll see in critical computing. How many of you have heard of critical computing? Okay, two, okay, three. Okay, that's actually a higher amount than I expected. Because critical computing is very much focused on how yeah, how algorithms and culture kind of intersect. And the other one is human computer interaction, which we'll talk about more in session three. Um, yeah, these ways of conceptualizing fairness are tend to be a bit different. And yeah, and if you take any like algorithmic course which is focused on fairness, you'll basically be just focused on weak fairness. So yeah, now we can kind of move on to like some general techniques to reducing fairness. This session will be a bit quicker. Um, Here, this is just like an exercise to make you think about like biases and unfairness. So suppose a university has the following admissions, where men overall have higher admission rate of 6%. Is it fair to claim a gender bias in admissions in this case? I don't know how, I think you can all sort of see it. So yeah, basically it's saying like, is it unfair because the percentage of admitted men is like 6%, while the percentage of admitted women is like 22%. And this might take a while to like to look at to like see. Um, but yeah, does anyone have any initial thoughts? Go ahead.
Want to why the 6% and 22% women? Was it because the men had higher average school, for example, or is it because the competition stable was, for example, 9%? What's possible?
Yeah, that's really good. It's like a part of it is being having that awareness. Like to in order to answer that question, you need to have awareness of like what is the systemic procedure in which that decision was made. Yep. Anyone else? Oh, yep. Yeah, I guess that could also be a question of like what is the intention between why they're like having this disparity? Like, is it like this is the rate that they're at because it satisfies like a close enough threshold of closeness between genders or that kind of stuff? Does anyone notice like the any disparities between the number of applicants applying to engineering versus humanities across the different genders? Oh, okay. Mhm. Yeah, exactly. Like you have to have that um broader awareness and awareness of like what the discrepancies might be. Um, but yeah, like one of the okay, the statistical thing that I'm also pointing to here is if you look at the number of men that were applied to like engineering versus humanities, there's a very big like discrepancy in this instance where not a lot of the men apply to humanities. Also, this is also just like a binary thing of men and women, but disregard that. And there was more of an equal blend of like engineering humanities applying to women, of women applying to engineering humanities. But if you look at just generally the rates of people getting into humanities versus engineering, you'll see that it's the rates of getting into humanities is way, way lower than in engineering. So because the distribution of the amount of people applying to humanities for women is higher, then the amount of people that got admitted is overall lower. So this is like, so yeah, so it also beyond like systemic issues, you also have to kind of pay attention or look out for kind of what is the statistical cause? Like this kind of goes along with like what everyone was saying, but it's about identifying the cause as to why those discrepancies occur, because sometimes it's systemic and sometimes it's purely statistical. So to kind of like also illustrate some similar cases, can anyone identify what might be wrong with like the following two examples? Um, actually is
I don't know, it's like,
okay, sure.
um, probably find that that model is probably not the best one, because it kind of looks like these are better represented by some sort of clustering
Hmm.
rather than some sort of.
Yeah, exactly. So if you look at the thing, like if you apply the regression, it shows downwards, but you also see like five distinct sort of clusters kind of forming. So the model and within those clusters, there seems to be a relationship where it's like X, Y instead of negative X and Y. So depending on like the model that you use, you can get like different results. Um, like if you consider your data in its totality versus kind of creating different models and mathematically modeling different groups that you find, yeah, you can get totally different results. For the first case might be a bit hard to see, but pay attention to like the colors and which colors are represented in the sample. Oh, yep, go ahead. Yeah, exactly. So yeah, exactly. So sometimes when people take samples of the broader populations, they fail to kind of properly have many people of different like backgrounds or identities represented. So then that sample that you do have is very, very small. So it doesn't really properly represent um, that data within that given sample. So these are all like kind of sources of bias that kind of occur through statistical processing. So the first one is representation and collection bias. So it's like the data set that you create is not representative of the full population distribution. Second issue is aggregation bias, which is basically when you look at the broader effect of the group, um, that pattern that you see can be reversed when you look at data individually. Um, and yeah, and then I think some of the things that we're kind of talking about as well is like systemic measurement and historical bias, which is like bias that's related to the process of even like collecting and understanding the impacts of that data in the first place. So in terms of like weak fairness solutions, there's multiple ways in which people can reduce unfairness in the models. One of the easiest ways to do it is just like data set representation balance. So what this entails is just taking other like rebalances of the data set. Or another popular way that's being done modern day is synthetic data generation. So what that usually typically entails is, yeah, I think people are generally familiar with like synthetic data generation nowadays with like all the AI generated images and videos and stuff. But basically the idea is just automatically generate data based off of like characteristics of other data that you have. So then you just have a bigger data set for certain underrepresented like groups in your data sets. And there's multiple ways about going about creating synthetic data generation. Many times if it's doing it in a very like due diligence kind of way. It involves like really understanding the communities themselves. So then that's where like human centered AI and human centered interaction kind of comes in, where you can kind of introduce techniques such as ethnography, where you really understand the diversity of characteristics within certain groups and cultures and try to capture that within that data. Um, but there's also like very more simple ways of doing it where you just like for images, for example, if you want to balance that, you can just try to abstract characteristics with the image detection model, and then just try to like blend images together so that you just have a lot more data representations like in the kind of in-betweens between certain datums that you have. Another way of kind of increasing fairness is using non-sensitive attributes in the data. So just purely getting rid of sensitive attributes themselves is causes issues because usually there's some other forms of data that can be used as some sort of approximator of those protected characteristics. So like one of the famous ones is for like um, race and yeah, for race, for example, if in models where they took away like race as a characteristic as an input to a data into a model, it was usually able to kind of infer what the race was just based off of other information such as like postal codes and that kind of stuff, where it's like in certain postal code areas, maybe we have a higher proportion of certain people of certain races. So then it's able to kind of figure it out itself. So one way of going about this is using fair representation learning, which basically tries to optimize for the preservation of kind of the distribution of the data as a whole, but trying to remove holistically those kind of components out of the data. And then the other one is just like modify your approach to learning. So I'm sure, I think all of you have heard of linear regression, but there's like fairness regression where you just have as one of your penalties in your loss function, like basically metrics of unfairness. So it just ensures that your output doesn't have that fairness within it. But beyond weak fairness solutions, I think one of the more important ones that'll kind of be relevant when working around responsible AI is strong fairness solutions. So one of the main issues is like, is the algorithm even appropriate for the situation in the first place? Like, do we even require using an algorithmic solution with all the kind of like issues that might entail, like people not really understanding how to use it in the social context, or maybe the performance, the use of the algorithm itself kind of causing issues to procedural fairness, where it's like, maybe we shouldn't be using an algorithm and reducing people to just data in the first place within this decision-making context. The other one is like, does it like disrupt the social context in a way that causes unpredictability? So like in the case of Compass, this was like not the case. This caused a disruption because they didn't really consider what would happen if they use the algorithm in a way where they actually use it as evidence in their court cases. So they probably should have put more effort into understanding how people would react to the implementation of these algorithms in practice. And the other issue is like, does it robustly capture the social requirements of the broader system? Like, are the perspectives, values, and rights of certain social actors represented within that solution? And is there fairness, there are notions of fairness mathematically and ethically in alignment with like the actual moral wrongs and dangers that are happening within that system? Yeah. So yeah, that's it for the algorithmic fairness lecture. If you want to check out other things happening in UTMIST, you can check out the link tree. There's also a feedback form. So I read a bunch of the sign up form and what people are interested in with respect to um privacy and explainability. It seems like there's some people that are interested in more like technical stuff with respect to privacy and stuff. So I can touch upon more of the computational stuff and doing like notebooks for that, or I can keep things a bit more like conceptual. and theoretical based off of what people prefer. But yeah, if you want to give some feedback, you can fill out that form. So yeah, thank you so much for attending.